Thank you very much. So I think we can start if the speaker is
ready.
So it's a pleasure to introduce Gregory Chirikjian from Johns Hopkins University and National University of Singapore, who is going to talk about degenerate diffusions on unimodular Lie groups.
Okay, well, thank you very much, and thank you to the organizers. It's a pleasure to be here. It's always a risk inviting someone you don't know to a conference, so I appreciate you taking the risk. So I am that odd engineer mentioned in Professor Dooley's previous talk. So I am trained as a mechanical engineer and applied mechanician and taught group theory and harmonic analysis to myself, basically. And so I'll be talking about how degenerate diffusions on several different unimodular Lie groups show up in engineering and real-world scenarios. So this is more of an applied talk. So I'm not a mathematician. I'm not even an applied mathematician, but I do like to use modern mathematics as a modeling tool. And so I'm going to explain how degenerate diffusions on unimodular Lie groups arise in mathematical finance, in mobile robotics, and in DNA statistical mechanics. And in particular, what I'm going to be doing is using the Fourier transform on non-commutative groups, as well as a concept of Gaussian distribution on non-commutative Lie groups, which actually ties in somewhat with some comments from Professor Dooley's talk. This is a joint work with a number of collaborators over a number of years who are listed down here. So a little bit of background mathematics. So normally when I give talks, it's to engineering audiences and I'm educating them on mathematics, parsing in a way that they can understand. So I don't need to do that for you all, but I just want to sync the terminology. Well, first of all, I'll advertise my books, which are about applying non-commutative harmonic analysis, group representation theory, and Lie groups more generally in various engineering scenarios involving randomness, information, and motion. So by a unimodular Lie group, we mean one which is has an invariant measure, invariant under shifts on the left and on the right, and consequently it's invariant under inversion of the argument. I'm going to be using this terminology for the left and right invariant derivatives. This throws people off. I use R for the left invariant derivative because we're pushing on the right, and I use L for the right invariant derivative because we're pushing on the left. So if you read my books and say, no, it's completely wrong, look at the footnotes as to my reasoning for using this terminology. And sort of the canonical diffusion process on a Lie group will look like this. And if we want solutions to a system like this, subject to, say, Dirac delta function initial conditions, we can get it in a numerical sense by iterative convolution, on the Lie group. And what I mean by a degenerate diffusion is that this matrix of diffusion coefficients has determinant 0. So it has, it's not full rank, okay? So that's what I mean by a degenerate diffusion. Now, if we were in Euclidean space and you had a degenerate diffusion, then you would have, let's say, a Gaussian distribution propagating just simply by translation in that degenerate direction and diffusion in the other directions. Another little bit of notation, again, because I am an engineer, I like to associate the Lie algebra with Rn. So in other words, once you establish a basis for the Lie algebra and an inner product, I key that to the basis, the natural basis for Rn. So you choose your basis elements, capital EI, and there's a mapping, the V operator, which converts these Lie algebra basis elements into natural basis elements in Rn, okay? And so by an appropriate choice of metric, you can always do this. And so what that means then is, for example, the add operator can be thought of as the add matrix. And the difference between the operator and the matrix is I'll put brackets around it to denote it as the matrix, a matrix description or representation of the add operator. Now, we can, and this also relates somewhat to the previous talk, we can, in the Lie algebra, define, let's say, a distance. Well, in this case, it's sort of a directed distance. We can take the log of a candidate mean, mu inverse times g. If we take the log of that, that puts us in the Lie algebra. We take the vector of that, it turns it into a vector. And if we can find a mu such that this equation holds, we call it the mean of the distribution on the Lie group. And similarly, after the mean is calculated, we can calculate this matrix, which we call the covariance of the distribution U on the Lie group. And if U is time dependent as well, then of course mu is time dependent and sigma is time dependent. So this works very well for distributions that are somewhat concentrated around the mean. And, you know, I won't formalize exactly what that means, but at this point. And moreover, we can define a Gaussian distribution on the Lie group by defining the Gaussian distribution on the Lie algebra and essentially lifting it up to the group. Or you can view it as because we're taking the log, we're going down from the group to the Lie algebra to calculate these things. But in any case, you put a group element in and you get a number out. And so it's a function on the group, okay? So this is a closed, all of these things for the Lie groups that I'm interested in, which are mostly matrix Lie groups, are explicitly computable. And what's interesting is, and maybe you can enlighten me as to whether this is very well known or not, it was not well known to me, is that if you have a diffusion equation, you can propagate the mean to first order, in other words, as an approximation, propagate the mean by a simple concatenation of steps, and you can propagate covariance as well. And so if you have a continuous say, diffusion process, then you can, by calculating the mean and exponentiating, integrating and exponentiating, you can get a very good estimate of the mean defined in the previous page for a diffusion process. And likewise, the covariance can be calculated like this. And so what's interesting about this is that even if D is singular, it can be the case by applying this add on both sides and then integrating, the resulting covariance need not be singular. Okay, so in other words, there's a mixing that goes on for a non-commutative Lie group that does not happen in the abelian case. Now, having said this, I didn't show you the derivation of all of these equations, but it assumes that the group is unimodular. Okay, so there's a general tool here for looking at least at the small time or small diffusion, you know, if the norm of the diffusion matrix is small times time, if that whole thing is small, then this sort of approximation works extremely well. And I'll show you numerical examples. Now, when things are not small, then we have to pull out the heavier machinery and use Fourier analysis on the Lie group. And this is just like if you have a diffusion process on the circle. If for small time and small diffusion, a Gaussian on the line looks just like a Gaussian wrapped around the circle. But for longer time or bigger values of diffusion, then you either have to wrap around the circle many, many times, or you use just a couple of terms in a Fourier series. Okay, so that kind of duality exists as well on the unimodular Lie groups that I study. So for long time behavior, we look at the non-commutative Fourier analysis. For short time behavior, we use Gaussian distributions, and then there's a zone in the middle where we have to transition between solutions. Okay, so the first application I want to look at is finance, mathematical finance. And so this is what I call a baby example. because actually, okay, so if you look at the Black-Scholes formula, which is used in options pricing, it's not a diffusion equation. And it has, so here A is a non-negative or positive real number, really. And you have this A squared here, and you have this A here. Now, if you look at the differential operators, as I defined previously, for the case of GL1 plus, in other words, just the non-negative real numbers with multiplication of numbers as the group operation, then you get the differential operator that looks like this. It's one-dimensional. There's only one differential operator. It's abelian, so the left ones are equal to the right ones. And so what we observed was, if you take the Black-Scholes equation, you can massage it into this form, and instead of viewing it as an equation evolving on the ray, the positive real numbers, we can view it as evolving on GL1 plus. Okay, and if you do that, well, first of all, it's not a diffusion because there's that negative VR term, right? So you have this negative RV here. So it's a decaying type thing. But if we change coordinates like this and substitute in, we in fact get a diffusion process on a group. And what's nice about it, and it's on this group. And what's nice about this is that those pesky A squared and A terms have vanished. So this is a sort of a homogeneous diffusion process on this Lie group. And then we can take this diffusion process, we can put it into my Gaussian solution, which is an approximation, and then we get this solution. But what's interesting is that my approximation is actually the exact solution, okay? And you can compare this solution to the published one in the literature for the Black-Scholes equation. So that gave us some confidence. Okay, I want to move on to another case, mobile robots. So actually, I come from the robotics world. That's where I spend 85% of my time. And in robotics, the group of rigid body motions is the most important group. So this is a semi-direct product of the translation group and the rotation group. And this is the group operator. This is the inverse, the identity. In the planar case, we can represent these matrices as 3x3 matrices. Theta is the orientation angle, the SO2 angle. X and Y parameterize R2. The group law looks like this. But that's not, of course, that's not the only way you can parameterize. You could use polar coordinates for the translation, which in fact is actually is done when writing the irreducible unitary representations of SE2 in terms of Bessel functions, and going back to Vilenkin and Willard Miller and others from the 1950s, 1960s. And moreover, we can also parameterize the group using the exponential map. And so, in fact, the exponential map is surjective in this case. Okay, so here's an example. You have a wheelchair-like robot. We call it a kinematic cart. You have two wheels. The two wheels can turn independently. Now, suppose you ask both of those wheels to turn at a rate omega. Well, you can ask them to turn at a rate omega, but in fact, they're going to turn at a rate omega plus some white noise terms here. And so instead of just going straight at a speed r omega, where r is the radius of the wheel, so sometimes you're going to go this way, sometimes you're going to go that way. So in fact, this describes a stochastic process on SE2. And this stochastic process on SE2, there's a stochastic differential equation that describes it. And you ask, is that an Ito equation or is that a Stratanovich stochastic differential equation? And the answer is, in this case, we luck out. It doesn't matter. The Ito correction terms are 0 in this example. Now, if you run these stochastic sample paths and track the XY position, marginalizing over theta, just keep track of X and Y, you get this thing that over here, which people call the banana distribution, okay? Because it looks like a banana. So this is in the plane. Now the full distribution, including theta, looks like a twisted thing in XY theta space in the group. But when you marginalize over theta, you get this so-called banana distribution. And so now if we start with the stochastic differential equation, you can go over to this Fokker-Planck equation in coordinates, in x, y, theta coordinates. It looks like this. Or we could go back to the original stochastic differential equation and write it in a coordinate-free version. So G inverse times G dot is like the body fixed velocity, a joint translational and rotational velocity. And we take the V of this. This is a matrix times a matrix. I mean, this is basically a matrix in the Lie algebra for SE2. We take the vector of it. That makes it a vector. We've gone from the Lie algebra into R3. And what you see over here when writing it in this form is that you have a row of zeros. And this times its transpose, it's what's going to give us the diffusion matrix, which is singular. And so again, for, I've switched notations on you, sorry. Instead of calling them ER, I'm calling them XR because I copied and pasted from previous slides to put this talk together rather quickly. So these are the unit basis elements for SE2. This describes an infinitesimal translation in the x direction, infinitesimal translation in the y direction, and infinitesimal rotation around the z-axis. And we can recast the Fokker-Planck equation describing the evolution of this distribution as a diffusion process on SE2, okay? So you have a drift, which is to say r omega, you're translating in the x direction with a speed r omega, and then you have these two diffusion terms. But remember, it's a three-dimensional Lie group, and you have only two diffusion terms. The reason for that is because wheels cannot slide sideways, okay? There's a no-slip constraint, and so there's no diffusion in the y direction. So this is a degenerate diffusion, okay? Now, when we use the exponential coordinates for SE2, we can actually fit extremely well this distribution using this concept of Gaussian on the Lie group that I mentioned. So we published a paper in a conference, a robotics conference, and the title was "The Banana Distribution is Gaussian." And everyone said, no, the banana distribution cannot be Gaussian because it looks like a banana, whereas a Gaussian, the level curves look like ellipses. And the answer, of course, is, well, that's because you're using x, y, theta coordinates, but the banana distribution is Gaussian in exponential coordinates, okay? Okay, let's move on now to DNA statistical mechanics. It's basically the same diffusion process as that kinematic cart, except now there's no time in the problem, but there is arc length along a DNA filament. So you have a piece of DNA, maybe it's, I don't know, 5,000 base pairs long. It's in solution. It has resistance to bending and twisting, and it's being bombarded by the heat bath, okay? And so we can write down, again, a Fokker-Planck equation if we're describing the evolution of reference frames at one end of the DNA relative to the other end. So this is moving around at random, but there's a stiffness, local stiffness to bending and twisting, and there's a chirality to the DNA. The chirality gives us the drift terms. So here's the drift terms. And this is an inextensible model, so the DNA cannot stretch. So you get this drift, a unit speed drift over here. So the numbering for the basis elements for SE3 are 1, 2, 3 correspond to rotations, 4, 5, 6 correspond to translations. And so here what you see is that there are only diffusions in the rotational degrees of freedom. So this is very degenerate. And yet we can solve this system of, we can solve this sort of Fokker-Planck equation. But in this case, we're going to use the longer time limit and use Fourier analysis on SE3. So here the U's are irreducible unitary representations of SE3. Again, this is a unimodular Lie group. The theory for this was worked out many years ago. In fact, with an appropriate basis, the infinite dimensional matrix U, rather than the operator U, is something that an engineer like me can actually compute with, okay? And so, so we have a Fourier transform and inverse Fourier transform. And we have operational properties. And that's the key to applying the Fourier analysis to a diffusion equation like this, is that when you apply the non-commutative Fourier analysis to this sort of differential operator in the Lie group, you work through basically the same way you would in the abelian case, and you convert differential operators on the group into operator matrices in the dual space, okay? And we worked out what these operator matrices for SE3 are. And these deltas are Kronecker deltas, so you end up with very sparse matrices, which lend themselves nicely to computation. So here they are. They're in the various papers and books that I've written on these topics over the last 20 years. Now, the procedure goes then like this. We start with our diffusion equation. We apply the group Fourier transform to it. That converts it to a system of linear ordinary differential equations with constant coefficients in Fourier space. And the solution to that is the matrix exponential. Now, there's one hidden fact here, which is that these matrices are infinite dimensional, because this is a non-compact, non-commutative Lie group. But being an engineer, we took these infinite dimensional matrices, we truncated, we exponentiated, we truncated bigger, we exponentiated, and we found that there was stability of the sweet spot, okay? And then Professor Michael Taylor, a mathematician, came by a few years later and proved that it was okay for us to do that. So I like it when mathematicians prove that what we're doing is okay. Then, of course, after you have this Fourier solution, you can substitute back into the Fourier reconstruction formula, and this is what it looks like for SE3. Again, this is a 6-dimensional Lie group. We have 5 summations and 1 integral. Now, we can also handle things in DNA such as bent DNA. Suppose that you have a piece of DNA here, and then you have a bound transcription factor, a protein that binds to the DNA to bend it here, and then you have another piece of DNA here. So so suppose you don't know where this transcription factor is bound. Where it binds will bias the statistics, the probability density of the distribution of where one end frame is relative to the other. So in other words, with an experimental method, if you can keep track of where the 2 ends are, then you can get distributions and then seek to answer the inverse problem, where did the transcription factor bind? But in order to do that, we need first a forward model to say, if it binds here, or it binds here, what does the end distribution look like? And so what we can do is we can solve our diffusion equation for the first piece of DNA. We can solve our diffusion equation for the second piece of DNA. And then in between, we have this transcription factor imposing a rigid bend, which is like a Dirac delta function on this Lie group. So it doesn't, the translation is centered at 0, and the bend is a Dirac delta function on the rotation group. So we can do this convolution and we can get solutions. And in my papers, we published and showed what these distributions look like. So these are various papers going back, and I mean, this is almost 20 years old. This is 20 years old. This was our first paper showing that we could use the group Fourier transform to solve these kinds of diffusion equations. Okay, now I'm going to go back to finance, and this is probably the most mathematical part of the talk, because instead of looking at a baby example on GL1, we're going to look at another example. And this other example is what we call a lagging asset equation. So instead of the Black-Scholes equation, you get a modified equation that looks like this, with 2 variables, A and B, where A is a positive number and B is a real number. And you get, again, A squared, A squared, A squared. You get an A over here, an A over here, okay? So you get this partial differential equation. So we said, well, wait a minute. We had an A before. What's the next simplest group we can consider? Well, the AX plus B group, the affine group of the line, actually this is AF plus, so here A is non-negative. And the basis elements for the Lie algebra for this group looks like this. The adjoint matrix looks like this. And the invariant differential operators look like this. And you see, what gave us hope was that you have A's here multiplying these partial derivatives, and likewise you have them down here. So we asked the question, can we recast this equation in the form of a diffusion on this group? Let's back up. The answer is yes, but there's a problem in that the AX plus B group is not unimodular, so we cannot apply our tools. So what to do? So what we did was to bump up the dimension by a factor of 2 and construct different groups, okay? So it turns out that if you take a group and an element in the Lie algebra, you can define a semi-direct product like this. And so this is the tangent bundle endowed with a group operator, okay? And explicitly as a matrix Lie group, the elements look like this, where G is in the original group and X is in the vectorized version of the Lie algebra, which again looks like Rn. Now, that doesn't help. If the original group is not unimodular, this tangent bundle group will not be unimodular either. But what we observed, and you can tell me if this is a well-known result because I didn't find it anywhere, we can also construct a cotangent bundle Lie group, okay, which is also a semi-direct product. And the group elements look like this as matrices. We started with a matrix Lie group and we end with a matrix Lie group. And this group is unimodular, even if the original G is not unimodular. Now, it may not be surprising because it sounds like in statistical mechanics, you know, P, Q, you change coordinates, you don't change anything in phase space. But we didn't see an explicit statement anywhere of the unimodularity of the cotangent bundle group formulated as a semi-direct product. And so explicitly, we can define the Lie algebra basis elements for this Lie group, which are these tildes. So we take the little add matrix of the original basis elements of the Lie algebra. This is if you want to do the tangent bundle group, and we define a new V operator, which gives us a 2n dimensional vector instead of an n dimensional vector. In any case, we don't use the cotangent bundle group in this work. We use the cotangent bundle group, which is this. Okay, so this is a very general construction, and we have these very general results. If G is a unimodular Lie group, then this semi-direct product group, 2n dimensional, the tangent bundle group will be unimodular, and the cotangent bundle group will be unimodular regardless of whether the original group was unimodular or not, okay? So if this is known, please let me know because we didn't find it anywhere. Okay, so let's now look at the specific example of the cotangent bundle group for the AX plus B group. So this matrix right here is ad inverse. X and Y are the Cartesian position in the Lie algebra identified with R2. These are our our basis vectors for this Lie algebra of the cotangent bundle group. And these are the differential operators that we get. Now, what's interesting is, remember, our initial intuition was there were some differential operators here that we thought we could use when we were looking just at the group, not at AF plus. But this cotangent bundle group still has those, okay? And so what we can do is we can rewrite the original equation as a diffusion process on this cotangent bundle group, which is a unimodular Lie group. And then we can apply the same apparatus, the Gaussian distribution, etc., and get a solution for the small time limit. Now, if we want to go to the long time limit, we would need to use the Fourier transform for the group of matrices that look like this, which if I'm not mistaken, this is the Mautner group, okay? So we can do it there too, okay? Maybe you would call it XYZW normally, but A over B, B over A is a real number, 1 over A is a real number. So it's either the Mautner group or something that looks very close to it from my point of view. So there's an opportunity to apply Fourier analysis on groups to this problem as well. So all of this was published in a very recent paper, which is available online. It's an open access journal. So that's pretty much all I wanted to say. You know, we use a combination of Gaussian and Fourier solutions on unimodular non-commutative Lie groups. Here I demonstrated them in finance and in robotics and molecular statistical mechanics. And I'd like to advertise, I'm always looking for good postdocs, especially mathematicians or mathematical physicists who want to move into something more applied, maybe spend a couple of years with me on their way to going to work in finance or some other field or become an engineering professor. And I'll just do some more advertising of some recent success stories. Well, actually, the ancient success story of this was the co-author on my book. So this is now a Dover edition. Chirikjian here was a theoretical physicist who came to work with me as a postdoc, and then we ended up writing many papers together. And then Arash Ghani Farashahi, I believe, worked with Professor Feichtinger, and Christian Volker was another mathematician. So these are some other recent papers. We're looking in this one at the spectra of functions, of compactly supported functions on SE2, because, for example, if you have a robot arm, there's only so far it can reach. So the positions and orientations that it can reach live in a ball. And then in this one, we looked at, I mean, in a previous talk in this workshop, I heard people talking about crystallographic conditions. The crystallographic space groups are subgroups of the Euclidean groups. Here, we were looking at quotienting double coset decompositions, quotienting on the left by crystallographic groups, and on the right by a finite subgroup of SO3 to divide the Euclidean motion group into chunks. We call them shards. They're little Voronoi cells, and we're using that in my robotics work. And then again with Arash, we looked at, so if you take the quotient of SE2 by the Z2 translation lattice, you get a compact object, and that compact object we can calculate Fourier series on. And so that's what this paper was about, which was rejected from several places we sent it to, but nevertheless, we'll keep trying. So it's in the archive. So with that, I'll be happy to take any questions. I hope this wasn't too applied for this audience, but I tried my best.
Thank you very much. So judging by the discussion in the chat, it was not too applied for the audience. There was some already some questions there. So are there questions from the audience right now? Anyone who wants to start? In which case,
maybe I would like to thank you for anyhow enlightening us very pure mathematicians with I don't know, well, showing us that, say, non-commutative harmonic analysis is really used in applied research in robotics, finance. It's pretty cool to see.
Well, thank you, David. Actually, it's not used all that much. I considered myself an ambassador to try to inject it into engineering, but the amount that it's used, it's few and far between. But I'm hoping that there's more and more. Certainly in the robotics world, if you meet a roboticist, most will know SE3. They will at least know that the group of motion, it's a Lie group, etc. Most will not know Gaussians or Fourier analysis.
Thanks a lot. Anyhow.
So there was some discussion about the term Mautner group. I think Tony Dooley wants to say something.
I'd like to say I've read some of your books, and I have an engineering student at the moment who's doing a harmonic analysis on SE2 and SE3 project, and he's been to work to talk to the SLAM, simultaneous location and motion team in our engineering faculty, so I'm quite well aware of what you're doing.
Well, thank you. Yeah, so that's an area where they do understand Gaussians on SE2, I should say, yes. And I have some friends there as well, so maybe I'll see you the next time I visit.
My aim is to subvert engineering students and bring them to mathematics.
Well, we can have a tug of war then. I'm going the other way.
Going the other way as well, I think, actually. I don't think that's the Mautner group that you described, actually. But
okay.
Perhaps we can talk about that offline. The other thing, I really wondered when you made a big thing about these groups being unimodular, why is it so important to you that they're unimodular?
Well, that's a good point. Maybe there's a way to modify the formulation that we've done in the past, but there are some steps where the invariance of the integration measure under shifts plays a role in some of the derivations, and that's for the Gaussian approach. For the Fourier approach, I don't even know how to construct Fourier analysis on non-unimodular Lie groups. I mean, people talk about wavelets and things like that, but you all would know better than I how to do that.
Sure. Well, come to Sydney and spend a month, and I'll tell you.
Okay.
I have a short comment about this embedding into unimodular groups. So I think there's I'm not sure whether this is really solves any problems or makes things easier for you. But if you have a non-unimodular group, you can always write down a semi-direct product group of this group with a normal factor of R that acts just by the right power of the modular function, and you get a unimodular group. So you can embed any unimodular group into any non-unimodular group in a unimodular group extension by just a one-dimensional extension. It's not a big deal.
Yeah,
that's
okay.
Essentially, by you just write down the formula for the modular function of the semi-direct product, and you can guess the power that you need for that. And I'm not sure. I mean, to me, somehow actually the cotangent bundle looks like a much more interesting object to do analysis on. Maybe that solves more problems for you than just embedding it into a unimodular group, because that's also my impression that this part doesn't really, to me, that's intriguing that that's such a big deal. I would concur with Tony Dooley there.
I think that probably you can prove the cotangent bundle thing by using the extension that Hartmut has just described, actually.
Well, the proof for the cotangent bundle being unimodular was very straightforward. Yeah, if you're saying bumping the dimension up by 1 and including the modular function would do the trick to make it unimodular, that's something that we could look at. Yeah. If you have references or textbooks or whatever or papers, it would be great to see that written down.
I can write them. I'm not aware of any particular textbook. I've never looked at this, but never looked for a reference there. But that's just something I stumbled across.
Well, we'd like, if we use it, we'd like to give appropriate credit. Yes. So yeah, or maybe we write a paper together using that the next time.
Maybe it's in Hans Reiter's book. Do you think it's in Hans Reiter's book, Hartmut?
I'm not sure, but it's possible. At least it's possible. I may have to look at other books. Maybe it's a remark somewhere, but it's certainly. I mean, I think probably the best reference, if you want to look at it, or if you want a quick reference, is look at the book by Hewitt and Ross on abstract harmonic analysis. They have an explicit formula for the modular function of semi-direct product, and from there it's just one-liner essentially.
But isn't that they focus on compact Lie groups? No.
No. Hewitt Ross part 1. That's very general.
Okay.
And they talk about group extensions and all that stuff and semi-direct products, and you just look at the formula there. So it's just the, well, I mean, modular functions of the two groups involved, and then the modular function of the group action of the one that acts on the normal subgroup.
Yeah.
And that's,
I think it's in volume. I think it's in volume 1 somewhere, actually.
yes.
Okay, I can look there.
I think it's not in Hans Reiter's book. I think he doesn't talk about semi-direct product. Also, it's good for me to meet Gregory, because Arash was really in Vienna, and he got an individual Marie Curie fellowship, and he's now spending time in Leeds. So I mean, moving from mathematics to engineering and keep the connection is certainly a very interesting path for young and application-oriented people. Yeah.
Okay. It's a pleasure to meet you in person or virtually, rather than through Arash.
Yeah.
Okay, I think we have one more time for one more question, and then we'll probably conclude the session.
I would like to ask about, like, is there any application in aerospace engineering? Because I moved from aerospace engineering to mathematics.
Aerospace engineering, certainly satellite attitude dynamics. So you have a satellite and it has orientational dynamics, and you want it to point in a certain direction, and there may be some randomness there. That would be one. So state estimation, and that's related to this field of SLAM, simultaneous localization and mapping, that Professor Dooley mentioned, where you have sensor measurements and they have noise, and then your physical system has noise, and both are described by probability distributions, and you use Bayes' rule to merge them together to get the best estimate. So there's that, and then the kinematic cart model that I showed is quite similar to aircraft models. So you have an airplane, let's say, with 2 engines, and you have ailerons so that you can move in 3D, but it's very much like the no-slip condition, and you can have things go way off, like that flight that disappeared from Malaysia, right? I mean, the estimate of where it might have landed in the world would be use methods. I mean, I wasn't involved in it, but it could be, we could use methods like this to estimate where it might be by having a diffusion process propagate out from where it was last known to be and its heading to look for the most likely location.
Oh, thank you. It was an interesting talk.
I was once on an aircraft where the engine exploded.
Oh.
And it was very eerie because the aircraft moved sideways. And I'd never felt that before in an airplane. You're used to them going straight ahead, but
yeah,
there was a bright flash and the right wing exploded and it moved sideways. Then we turned around and landed back in Bangkok.
wow.
But,
Well, okay, so I stand corrected about the aircraft not sliding sideways, but hopefully it's a rare event.
Hopefully it's a rare event, yes.
Okay.
Anyway, nice talk. Thank you very much.
Okay, thank you.
Thank you also from my side, and thank you for the participants in the discussion. I think it's time now for everyone to grab a coffee. If David wants to add anything right now, it doesn't seem to be the case.
No, thank you. So I will just meet again at 10:40.
Okay, so thank you very much to everyone.
Yeah, thank you also from our side. And thanks to you, Helmut, for joining the session.
Tschüss.